And we're on, all right. So back in weeks 6 and 7, after we did the probability, we played with the idea of confidence intervals using sampling distributions with a simulator called StatKey, and then we proceeded to do simulations for hypothesis tests. So that's like rolling the dice over and over again to try and figure out what the probabilities are, which is fine and appropriate, and sometimes that's the only choice when it comes to exploring reality by doing experiments. But there's this theory behind it. Like with a dice, we have the theory that 1/6 the time we should see the number 4. Now that's a theory. If we had all dice rolls ever rolled and ever to be rolled, then we would see exactly 1/6 of them, but that's not possible. So the reality and the theory are related, obviously. The theory is ideal. It's like finding a perfect circle in nature. One does not exist. It's just this idealized form our minds have kind of developed from what we experience. And so now we're going to take the theory of normal distributions, excuse me, and the central limit theorem, which give us some formulas and equations, and we're going to apply those to the confidence intervals and hypothesis tests. So now basically we have 2 ways to come up with hypothesis tests results and 2 ways to come up with confidence intervals. So I'm just going to kind of draw a flow chart of what we have for inferential statistics so far and a few of the formulas, and then we'll apply them to a few problems. And let's see, we have a new visitor. Cool. All right, so whiteboard. And good morning, Jennifer. So here's kind of the overview of inferential statistics. So there's essentially 2 parts to statistics. Descriptive statistics, where you get data and you make calculations like mean, median, mode, standard deviation, and you make pretty charts and graphs. That part of statistics is important, and we covered most of it in 3 weeks. Inferential statistics is the idea of using data, using samples to make predictions about populations, and inferential statistics is a vast, vast subject. That's the majority of what statistics is really about. And people spend, like they get PhDs in just inferential statistics. But descriptive statistics, that's like 3 or 4 weeks of stuff to learn. So we're scratching the surface of the real big part of statistics. So for us, we have 2 main parts of inferential statistics. Either we're trying to find some value about a population, and that's when we make a confidence interval. And so again, here we're trying to identify a population parameter. Okay, so that's one part, and that's done all the time, especially for public opinion surveys. We want to know, well, what do people feel about things, or what do people believe about things right now? The other part of inferential statistics we've explored is the idea of testing something we thought we knew about a population parameter, and that's the idea of a hypothesis test. And in this case, we're trying to test a value of a population parameter. Whoa, what happened to my pen? Stop it. Interesting. Let's try that again. So for example, there's a lot of unrest right now related to some recent deaths in society in the US, and there's all these marches going on. And how do people feel about the National Guard being called in to help maintain order? So we don't know. We're going to have to ask a lot of people and figure that out. We might have some biased belief based on our preconceived ideas that, yeah, we should throw in the National Guard, and everybody else agrees with me, and somebody else might say, oh, no, we shouldn't do that. And everybody else agrees with me because I hang around with people that believe the same things as me, right? We're all biased. So we have to find ways to measure these things. So again, identify some unknown information And then otherwise, somebody might say, hey, it's 50% of people think we shouldn't use the National Guard. Okay, well, let's take a sample and double check to see if that's really true. So a hypothesis test tries to take some given information and say, is it really true or not? Does the data support it? Does the data not support it? Do we reject the null? Do we fail to reject? So testing existing information. Okay. So once we decide which branch we're on, what kind of problem we're trying to solve, then we have to decide in each of these, are we playing with a mean or a proportion? Now there's tons of other parameters to measure, like standard deviation, the median, percentiles, and things like that, the range of values that you could get for a certain measurement. So there's tons of parameters one could measure. We're only focusing on means and proportions. And again, if you were in some subject where you needed to explore more than that, then you would get more statistics in your background. So once we decide, hey, yeah, I'm doing a confidence interval, then we want to know, are we working with a mean or are we working with a proportion? Okay, so like the percentage of people who think it's okay to use the National Guard to deal with these marches, this public unrest over what's going on right now. Now, as far as a mean, there's a couple of things to consider about the mean. So that breaks, let's see, now I guess I want to stick with, no, I'm going to use 2 different colors. There's 2 different parts we might explore as far as the mean goes. And for the mean, remember the symbol sigma stands for the population standard deviation. And so the question is, do we know the population standard deviation, right? And I shouldn't put a question mark there. Let's say we do know it. The other scenario is where we do not know. So don't know sigma, which again is the population standard deviation. Now think about this for a second. We're trying to measure a population mean. If we don't know the mean, how would we know the standard deviation? So although in statistics class like this, it's usually taught this way first, kind of because it's easier, in reality, it turns out this branch doesn't hardly exist. So we're not going to, we've gone down this branch a little bit. We will this week, but it's not going to be very much used. Otherwise, we don't know it. If we think we do know it, then we're going to use a normal distribution. And if we don't know the population standard deviation, we're going to use what's called a t distribution. That's a funky T. Let's try that again. T distribution. And so more often we're going to use the T distribution. And the T distribution is kind of cool. It was developed a little over 100 years ago by a guy that was working for the Guinness Brewery, trying to maintain quality with a small number of samples to try and figure out if they were doing a good job making the beer, what conditions were right for the yeast, how they reproduce the yeast, all these different things that go into making a beer consistent. It's very hard. And so 120 years ago, people were working seriously on this kind of problem, and mathematicians or people that knew a lot of math worked for these companies, way back then, trying to make sure they had something good people wanted. And the T distribution came from that, which is kind of neat. So formulas, if we end up down these paths, are for a, let's see, we're under confidence interval. We have a margin of error. So the error bound on the mean is what we care about most here. That would be a particular z-score that we have to calculate times the population standard deviation divided by the square root of n, according to the central limit theorem we learned last week. The t is pretty similar. If we happen to not know the population standard deviation, then we have to calculate a t-score, and we'll look at how to do that in a moment. And since we don't know sigma, we have to use s, which is the sample standard deviation, and then divide by the square root of n. So notice these formulas are pretty similar. A z-score counts standard deviations. A t-score does it in a slightly different way, but similar. Then we have a standard deviation, and then we have square root of n, okay? and mostly we'll end up down this path here. So if we don't know the standard deviation of the population, in another case we'll use this as for small sample sizes. So the central limit theorem says even if you know the standard deviation of the population, you still want to have a sample size n that's greater than or equal to 30. It turns out that even if you know the sample standard deviation, if you have a small sample size, you're not allowed to use a normal distribution, so you use a t-distribution instead. So over here, another case will come down this branch as if n happens to be less than 30. Oops, that didn't come out right over there. So this is kind of a flow chart about how to proceed. And the flow chart still kind of applies to the way we did things in StatKey. It's just in StatKey, we don't need these formulas here. StatKey does the computations for us accidentally on purpose, which is kind of neat. All right, so again, this is, oh, this blue thing right here, by the way, I didn't label it, is the error bound on the mean when we don't know the standard deviation of the population or the sample size is small. As far as proportions go, we had a rule about the proportion that the successes, which is the probability of a success times the number of total outcomes, the book called this X also, that number has to be greater than 5. And the number of failures also has to be greater than 5. And that would be Q times N. So if these two conditions are true, then we can proceed. If those aren't true, then we're stuck. We can't do it without some other kind of statistics that we haven't explored. It's in a whole nother course. And Q, remember, is always 1 minus P. And then to calculate the error bound on the proportion, then we're going to take the appropriate z-score, which is kind of the same thing as the z-score in red over here, and multiply by the square root of P times P prime, because it's a sample, Q prime over N. And all of that is inside the root. Redraw that better. Start it like that and put parentheses, P prime, Q prime over N, close the square root. And yeah, so then we got to learn how to find the z-score, how to find that t-score. And I don't think I'm going to fit it in this screen right here, but we'll find that next. All right, so otherwise, if it's not a confidence interval that we're doing, I'm just going to kind of draw a little line down here, separating these two. In a hypothesis test, it's either a hypothesis test for a mean or a hypothesis test for a proportion. And then kind of like the confidence interval, either we know sigma or we don't know sigma. Oops, I didn't want that to be in red. So I'm putting that in red just to indicate that often, come on eraser, often if we're questioning the mean or we don't know it, how the hell would we know the standard deviation, right? It just doesn't make sense. But it's taught that way because it more easily relates to the central limit theorem, which is a little bit complicated. So let's see, this is again, don't. No, sigma. And remember, sigma is the population standard deviation, not the sample standard deviation, not the sampling distribution standard deviation. Those are 3 different things that are related. Okay, so let's see, what else do we need to know here? If it's a hypothesis test, then we need to know the standard error, which is standard deviation of the sampling distribution. And let's see, what else do we need? I guess that's the main thing we need to know there. Standard error, SE, and that would just be sigma over the square root of n. And we're using a normal distribution. If we don't know sigma, then the standard error is the sample standard deviation over the square root of n, right? Notice same thing that's going on over here. This is my standard error right there, s over the square root of n. So if I don't know, I need that right there, and this is from a t distribution instead. And we can either use a stat key or a spreadsheet to do normals and t distribution calculations, which we started working on last week. Anything else I need to mention there? I think that's good. And again, with the hypothesis test, the main thing we're trying to figure out is what's the p-value. And I'll review what a p-value is in a moment. Proportions, same rule over here, successes and failures have to be greater than 5. So as long as NP is greater than 5 and NQ is greater than 5, and again, these are successes and failures that are counted. Oops, missing a letter there. So if that's true, if I can check off those boxes, then I can proceed. And then here, I need to know the standard error. And in this case, the standard error is going to be P times Q divided by N. And all of that is in the square root. And notice that almost the same thing as over here. Notice in the confidence interval, it's a P prime Q prime. And the importance of that right there, those are sample values. If we're talking about a confidence interval, and if we're talking about a hypothesis test, then it's important that we switch these to the population values, the population parameters. And hey, Dawson, I didn't get to welcome you. How you doing? Welcome to class. So this is a flow chart of the major things that we've covered in the last 4 weeks, including this week. No, 4 weeks. 4 weeks, including this week, yeah. And we were doing this already in week 6 and 7. We just weren't using these formulas down here. And I don't know if you can see what I'm pointing at here. So we were doing all of this in week 6 and 7. So this is week 6 stuff. This is week 7 stuff. In week 8, we just added these formulas in addition to using stat key. So before we were bound to stat key, we didn't have any other way to proceed to do a confidence interval or a hypothesis test. Now we don't need stat key anymore, but we can still use it if we wanted to. So we have 2 ways to make this stuff happen. And